I am Mr. Ish and I'm welcoming you to this video where we build upon the concept that we discovered and we learned in the previous video. You remember that it had to do with change in concentration over change in time, a mixing problem involving differential equations, and that's exactly what we have here. In that previous video, the tag of which I will include with the information section of this one, we were looking at concentrating a solution. Here we're looking at diluting a solution. So the question goes like this. We have a brine tank which has a volume of 1000 liters. It has 20 kilograms of dissolved salt. Now in this particular instance, pure water is being pumped into that tank at a rate of 10 liters per minute, and the tank drains it from the other end at the same rate. We have to find the concentration at time t, we have to find the concentration after 20 minutes, and the volume is kept constant. I want you to think about everything like this. You have a tank over here which is 1000 liters of brine, and you know brine is very concentrated. It has 20 kilograms of dissolved salt. You're now, in this particular instance, you're bringing pure water in here, which is 0% or zero of anything with regards to salt. It's being pumped in here, and then it mixes up, and then you're getting a dilute concentration which is coming out. The same rate coming in, the same rate going out. Volume is always kept constant. We have to determine what is the concentration over here at any given time. What will be the concentration? By now you have realized this particular differential equation form, the change in concentration or change in time, this variable c can be anything which you want it to be. I'm using c because I'm used to using it. Is always equal to rate in, what's coming in, minus the rate out. In this video we will formalize more what this is. Let me just for this few minutes talk only about the units, how the units play. And imagine you have something coming in here, not regards to what you see over here, but very generally something which is concentrated like 1 kilogram per 1 liter. That's the concentration coming in, but it's coming in at a specific rate, and the rate you know would be 10 liters over here per minute. I'm just borrowing this value right over here. But look exactly how the units handle each other out. You have this cancel out with this, and you end up seeing here 10 kilograms per minute. And what does this unit kilogram per minute imply? It implies rate. In the previous video we were not very formal with regards to the units, and we kind of threw them out of the window. But you can see how this means a rate. It's not definitely just a concentration, but it's talking about concentration volume, but it's also talking about time, hence that word rate. But this is exactly how you see the units would come in. The volume cancels out, you have kilogram a minute, which implies the rate. Anyhow, now we dispense with the units and let's get back to the question. What exactly is coming in to this chamber or this tank? We have pure water. What is pure water in terms of concentration? Think about it. Pure water has got absolutely no brine in it. If you had pure brine coming in it, it would be 100% with regards to brine, but you have pure water, so it's 0% with regards to brine. In terms of concentration and in terms of the flow rate, we have 10. It will all zero out, but that's fine. It will zero out, but don't get confused by that. Rate out, what's coming out? Well, we have a certain concentration which will come out of the tank, which is slightly diluted now. Originally it's brine, but now as the water comes in, it's diluted. We don't know how much is diluted. It's a certain variable c, and it is found within a certain tank which has a constant volume 1000 liters. You see, I'm not talking about units, but you should always keep them in the back of your head, and you have the rate here. With regards to units, you know the liters would cancel out, and you'd have something over here in terms of c kilograms per minute, and that's exactly what I was alluding to earlier, but I'm not being formal with the units. This right here is exactly my differential equation, which has to be now solved. You'll have dc over dt is equal to, this zeroes out, you'll have c minus c, don't forget the minus c over 100. This is my equation which I have to do. Again, separation of variables. Take the c onto the other side. I'll keep the minus over here. I'll have 1 over c dc over dt is equal to minus 1 over 100. I'll integrate this with respect to dt, and you'll see the dt's cancel out, and you can integrate this, you can integrate this. When you integrate this, you're getting natural log c, not too hard. When you're integrating this, you're getting a minus t over 100 plus your constant of integration, which I have formalized as that, c1. You can stop right here if you want. I'm in the habit of converting things into exponential functions because at the end I want to talk about a possible limit. It'll be easier to evaluate a limit with an exponential than it is with this. C is equal to, you take the exponential of everything else, minus t over 100 plus c1. C is equal to e to the minus t over 100 times e to the power of c1. You see I've split them up using the properties of exponents. Now, how do we get to this right over here? We get to it by thinking exactly what the initial conditions were. Initial conditions are 1000 liter of brine, which is 20 kilograms of dissolved salt. But with regards to time, if you have a concentration at time 0, you have exactly what you started out with regards to your brine, which is 20. C0, concentration with respect to initial time 0 minutes, is equal to 20 kilograms of dissolved salt. And that's exactly what you put right here in this part. And what we will do is solve out for that C1. We can solve it out. C here is equal to 20. E to the power of 0 is nothing. You have e to the power of c1. c1 is equal to natural log 20. And that's exactly what your constant of integration is equal to. Everything over here is nothing new. It's just properties of logarithms at play. Now, let's formalize our function and answer this question. This question is already solved almost when I present the answer to you right here momentarily. Our function is exactly the concentration at time t, which is what I'm putting for you right over here. Concentration at time t, you see how this C has become concentration at time t? Simply because we brought this into the picture, is equal to what you see over here, e to the minus t over 100 times e to the power of natural log 20. But you know e to the power of natural log 20 is something like this, e to the ln x, which is equal to x. And this figure, which is equal to 20, I can bring right here at the very beginning, and I will do so. Finalized manner, our concentration is 20 e to the minus t over 100. This right here is my function, and this answers this part right here. What's concentration at time t? It's this. I prefer to look at this type of equation in this form with the constant of integration brought into play right here as 20. So now let's answer our next question. You'll need the calculator for this. What's the concentration at 20 minutes? C20 is equal to 20 e to the power of minus 20 over 100. You know you'll do the calculator strokes over here. You'll do 20 divided by 100 minus, it's minus 20 over 100, exponential function of that, multiply this by 20, and you'll have 16.37 kilograms. And what does this mean? Well, you know you initially started with 20 kilograms. As you're pumping in water, as some of that solution is being exited from the other side of that tank, equal rate in, equal rate out, you know this will get diluted, but it won't dilute at a very fast rate. It'll dilute at a steady rate. Whatever that rate is, based on the differential equation, we now know that we started with 20, but now after 20 minutes we have 16.37 kilograms of dissolved salt. So we've definitely lost some salt here by means of the dilution process, which is fine. That's fine. Now let's look at a very quick limit here. Limit as t approaches infinity. I don't have it mentioned here, but we'll do it anyways. Limit as t approaches infinity. This is why the beauty of this function is you have exponential. You evaluate it by means of putting infinity in place of t. You're looking at 20 e to the minus infinity. Infinity over 100 is just an infinity, which is same thing as 20 over e to the infinity, which is basically 20 over infinity, which is 0. What does this limit as t approaches infinity in terms of time mean? Meaning after an indefinite period of time, all of this dissolved salt will have zeroed out, and you'll have 0 kilograms of dissolved salt in your tank, because you're constantly pumping in pure water and you're constantly losing some of that solution. Eventually all that will remain will be just pure water, and the brine will have been lost. Your tank will approach in terms of dissolved salt 0. And that right there will bring us to the end of this video, and you see how the dilution played out. Perhaps the most tricky part for students here would have been this specific part right here. Pure water is 0, and then it would zero out all of this. The rate in will zero out. The only thing which you will have coming in is basically a rate out in terms of everything which will go through the solving of the differential equation process. But that's it for this video. Thank you for joining me.